So the basic setup I'm going to consider is, let me move this little thing. So, and can everyone see my mouse?
Yes.
Great. So the basic setup I'm going to consider is a very standard one. We're going to think about two random variables, an input X and an output Y, and some stochastic map that relates them. So these could be, for example, the input and output of a neural network, or it could be the past and future of a dynamical system or stochastic process. Or it could be anything, but generally Y is going to be the thing that we care about predicting, and X is going to be the thing that we somehow can have available in order to predict Y. And a very central concept in my talk is going to be the concept of minimal sufficient statistics. So we say that some function of the input X, so here I'm going to write it as a deterministic function, f of X, is a minimal sufficient statistic if it satisfies these two properties. So first, if I condition on f of X and I look at the distribution of outputs Y, it's the same as conditioning on both the input and f of X. So a sufficiency basically says that f captures all the information there is to capture about Y that is contained in X. And the second condition, so there's many actually sufficient statistics. So for example, when f is the identity map, that's of course sufficient because that's always going to capture all the information in X about anything. But we also look for the minimal sufficient statistic, and the minimal sufficient statistic means that f is a function that can be written as a function of any other sufficient statistic. Okay, so it can be, so we can take any other one, kind of compress it with this deterministic function and get f. And this actually defines minimal sufficient statistics uniquely up to permutations or invertible transformations. So as I mentioned, this is a very kind of fundamental notion of what it means for to capture the minimal information in X about Y. And I'll also mention that in dynamical systems, these minimal sufficient statistics are called causal states. And there's been a lot of interest recently with the work of with the simplex group of trying to find these causal states in things like transformers, for example. So there's also a different information theoretic characterization of minimal sufficient statistics that will be useful for our purposes. And basically, we can say equivalently say that a minimal sufficient statistic satisfies two properties. So first, the conditional mutual information between X and Y, given that statistic vanishes. So again, it captures all there is to know about Y in X. And minimality now has this somewhat simpler form, which it achieves the minimal mutual information between the input and this deterministic function of the input. And this suggests, why is it useful to have this information theoretic characterization? Well, it's kind of, both of these are quantitative properties now, and they're both stated in terms of information theoretic terms, and it suggests some ways that we can derive what I'm going to call approximate minimal sufficient statistics. Maybe I'll just call them approximate statistics for short because it's a mouthful. Because we can kind of quantitatively weaken these requirements, and we can achieve approximate sufficiency. And what approximate sufficiency is it gives us a kind of optimal ways to coarse grain X, given that we want to preserve some information about Y. Because actually minimal sufficient statistics is a very, very kind of conservative concept. So if the smallest change in the distribution of Y when we change X is gonna make it's going to change the sufficient statistics. So it's not very robust, and it's very conservative. And also estimating it from data requires actually well, in the limit it would require it can require an infinite amount of data. So I'm gonna basically refer to this problem of finding approximate minimal sufficient statistics as information theoretic coarse graining. And why might we want to do this? Well, one of the things is, I was kind of like many of you, I think, were interested in these recent findings by Simplex, and where they found that transformers have, for example, belief state geometry, or seem to represent belief state geometry internally, which are causal states. Basically, it's a representation of causal states. And so I was kind of been interested in trying to uncover this, but for much richer data sets rather than kind of very, very toy, very simple stochastic processes. Can we do it for kind of real world, maybe time series data? And what would those causal states look like? Well, we're probably going to have some kind of optimal coarse graining that's going to reflect even the fact that we don't have infinite data, but we have a finite amount of data. Another thing is, by varying this, as we'll see, we will kind of, in several cases, we'll explore this trade-off between compression and prediction. And by varying this trade-off, we'll see that it may be possible to uncover kind of inherent scales in the system. So when, as we compress it more and more, when do we really start to lose some kind of structure predictability? And I'll also mention that this quantification of sufficient statistics has been proposed as a kind of information theoretic measure of complexity in these input-output maps. And also, in terms of interpretability, we might want to find these kind of use approximate statistics as a kind of coarse graining that optimally sort of blurs the input while preserving information about the target. And so this is related to the idea of the renormalization group in physics, where we might want to take some very, very high dimensional microscopic system, and we want to blur it in some way so that to preserve some kind of relevant aspects about, let's say, macroscopic behavior. So usually, this is a figure from this paper. Usually, in physics, this has been done in a somewhat ad hoc way by designing different kinds of rules, maybe um, to blur things like lattices. But recently, there's been this idea that maybe we can use kind of more principled ideas from information theory to find, let's say, the optimal way to do so. Great. So what I'm gonna try to maybe not answer, but at least ask in this talk is, how do we best define these approximate statistics? How do we find them in really large systems? And how do we interpret and visualize the coarse gradings that they produce? Great. So before I go on, is there any questions by any chance? So the usual way that that this problem has been addressed in the field is using something called the information bottleneck, which I think some of you are going to be familiar with. So as I mentioned, in a minimal sufficient statistic has this information theoretic characterization that it achieves zero conditional mutual information, and it has the smallest between X and Y, and has the smallest mutual information with the input. So information bottleneck proposes to essentially weaken these conditions. So by doing two things. First, instead of looking for deterministic functions of the input, we're going to look for stochastic maps that map from the input to some coarse-grained space Q. Sometimes this is called the bottleneck variable. And so basically, we go from deterministic to noisy coarse grainings, and we're also going to weaken the sufficiency requirement. So we're going to say, okay, well, we don't require perfect sufficiency, so we allow Ada a finite amount of information to leak through the bottleneck variable, because hopefully this will allow us to achieve a much lower compression. And if we write the Lagrangian for this problem, this basically constrained optimization problem of minimizing the mutual information and under some constraint on the conditional mutual information, we get this expression. And we can use a standard information theoretic identity to rewrite it as this very nice objective. This is the often called the information bottleneck objective, which is a kind of trade-off between two terms. So the first term tries to minimize the mutual information between the bottleneck and the input. This is the compression term. And the second term tries to maximize the mutual information between the bottleneck and the output. So this is the kind of prediction term. And this actually gives us a curve of possible solutions. So as we vary beta, which controls the trade-off between prediction and compression, we recover this kind of curve where as we increase the amount of mutual information between Q and X, so this is kind of compression, the compression axis, we can get better and better predictions. Sometimes it's called relevance, and we trace out this curve of basically feasible solutions and non-feasible solutions. And all points on this curve can also be parameterized by beta. Beta sets basically the slope of this line, which is the trade-off between compression and prediction. So where also did this kind of idea come from? Well, in the original paper that proposed information bottleneck, which was, I think, maybe around the year 2000, it actually began from the concept of rate distortion, which is the classic theory of lossy compression that was developed, starting from the late 40s by Claude Shannon and then other people. And what rate compression says is that if we want to minimize some kind of distortion measure under an informational constraint on how much information we want to transmit across a channel, then we should minimize this kind of objective. So this is, for example, used in classic image compression, let's say, so things like developing JPEG. So there's actually, labs that study how people perceive, for example, errors in image compression. So in the setting of image compression, just to make things concrete, X might be the raw image, Q might be something like the JPEG representation of the image, which is going to have some visual artifacts in it when shown, and DXQ is going to be the distortion, which is like how bad is it to introduce certain artifacts. So, for example, maybe artifacts in color space are not as bad as artifacts in lightness and darkness. And so if we can construct this kind of distortion measure, then we can solve this problem and we get an optimal, basically, compression algorithm that maps uncompressed X to compressed Q. The problem is, how do we choose this distortion function? Because most of us don't have, psychophysical labs studying how people perceive things. And sometimes it's not even clear, what you would study if you had such a lab. And so what Tishby, Pereira, and Bialik, when they invented the information bottleneck, wrote is that, because the right distortion measure is rarely available, what we want to actually maybe consider is the prediction of another random variable, because that seems like a very, very common situation where maybe we don't have to design some kind of custom distortion function, but we can think about the problem actually of predicting a side random variable. And what they also showed is that the information bottleneck can be put into this rate distortion form, but the distortion function has some unusual properties. So the distortion function that corresponds to the information bottleneck is basically the Kullback-Leibler divergence between the predictions of Y given the, let's say, true input X, and the predictions of Y given the compressed variable Q where importantly, this decoding map, I'm going to maybe call this the decoding map, uh, itself depends on the encoding map. Okay, so we're going to have some coarse graining, and then this decoding map is going to undo that coarse graining by using Bayes' rule here. And then it's gonna, so it's kind of like, if we can undo the coarse graining to best predict y, what would be the Kullback-Leibler divergence? And this is definitely has the form of rate distortion, but it's not a standard rate distortion problem because the distortion function itself depends on the encoder. And so, for example, what this means is that it's a non-convex problem. It doesn't have, we don't have a simple or even not simple way, guaranteed way to solve it. And so there's kind of numerical issues, but I'm also going to argue that there's some conceptual issues that arise from this. So, right. So this is basically the KL is another way to think about prediction error here. And as I mentioned, it's not a standard distortion function. So what I'm going to argue is that information bottleneck is very interesting, and I think it's had some success, but it's also limited. Let me just also say what I mean by success. I mean, I think one of the successes of information bottleneck is it sort of sets a gold standard for compression, or at least in a certain operational setting. And you can compare real systems to that gold standard, and you can ask, let's say, how close are they to optimal? And so Bill Bialik, who's a very famous biophysicist, he's kind of done a lot of this, where him and his collaborators have looked at, let's say, real biological or neural systems and asked, okay, the internal representations that are they using, are they close to being, let's say, close to the information bottleneck curve. And this is an example from neurons in the retina where they argued that actually they are pretty close to this curve, suggesting that biology maybe optimizes some kind of similar objective. Um, some of you know this has also been an idea and a controversial idea in machine learning, whether machine learning optimizes this. I've actually written some papers about this, so if you're interested, we can discuss. But I'm actually don't want to get too deeply into information bottleneck stuff uh, right now. So I'm gonna say, like, despite these limitations in terms of what we're interested in, so things like, for example, AI interpretability, we might want to use, for example, try to use information bottleneck and look at the coarse graining maps that it produces. But here is where there's some limitations that arise that I mentioned earlier. So first, it's not really kind of possible to give a meaningful interpretation to this map, that the optimal coarse graining map from X to the bottleneck variable, because Q is kind of like just a dummy space, and the objective is invariant under permutations of this space. So for example, if we're compressing images, then Q is not going to have any kind of semantics or any kind of structure in it that would correspond to, let's say, pixels or locality or any other structure. And this occurs because, in a way, any permutation of Q, so that's a permutation of the encoder, can be undone and is undone by the, say, optimal decoder, which does the Bayesian inverse. And the other limitation is that it has this non-convex objective. So it's not even that it's kind of hard to optimize, it's that we don't actually know when we're ever at an optimum, right? So we don't know if we have reached an optimum. Usually what people do is like run this 10,000 times and choose the best. But it's also maybe, at least in some cases, it's quite unsatisfying. And both of these problems arise because, as I mentioned, the rate distortion is this non-classic distortion measure that itself depends on the encoder. Great. So what I'm going to propose is maybe a different way to actually think about sufficient statistics and approximate minimal sufficient statistics. And then this different way of thinking about approximate minimal sufficient statistics is going to actually suggest a different generalization that's based on standard rate distortion. And if I have time, maybe I'll also talk about optimal transport, closely related. So, but basically, it gives us a tractable and interpretable uh, and convex objective for doing information theoretic coarse grading. So, how do we proceed? So I'm going to start with a slight different definition of minimal sufficient statistic. It's completely equivalent to the previous one, but it sort of emphasizes a somewhat different aspect. So instead of saying a minimal sufficient statistic is a function over the inputs, we're going to say it's an equivalence class. And we're going to say that two inputs, x and x prime, are equivalent if they give the same, exactly the same predictions over y when conditioned on them. So we can also characterize this equivalence class now information theoretically, and it's gonna look a little bit different than before. So instead of having some kind of arbitrary space Q, we're gonna have a stochastic channel that maps from X, so this from the input space, again to the input space. So it maps basically from inputs to inputs. And as before, we're going to require first that it's minimal, meaning that the mutual information across this map is as small as possible. But there's going to be a constraint, which basically says that and there's several ways to write this constraint, uh, that the Kolbe-Kleiber divergence between y condition on x and y condition x hat on average is 0. So because this is non-negative, that means it's actually has to be 0 everywhere. And all this is saying is that basically, this coarse grading map only maps inputs to inputs with some positive probability if they give the same exact predictions. So the interesting thing about this, and I think this is, something that often happens in math, is that there's many equivalent ways to write something, one thing, but when we try to generalize that thing, those equivalent ways give rise to different generalizations. And so I think this is kind of one of those examples. There's many equivalent ways to formalize what is a minimal sufficient statistic. But those different equivalent ways give rise to different generalizations when we think about approximate minimal sufficient statistics. And in particular, we're going to generalize this to two coarse grading objectives, one based on rate distortion and one based on optimal transport. We'll see if I have time to talk about the second one, because I do want to have time for any questions if there are any. So, but let me talk about the one based on rate distortion. So, and I want to say that these are not unique. This is more like a family of generalizations, but let me talk about the one based on rate distortion. So, what we're going to do is we're going to say that we're going to consider coarse grading maps that map from X to basically a copy of the same space, X hat. We're going to minimize the mutual information, and we're going to penalize this distortion, where the distortion is just given by the Kolbe-Kleiber divergence between x and x hat. And so we can think of this in comparison to, for example, information bottleneck, is we want to compress x, but we're going to predict y with a fixed decoder. So we're not going to sort of do any kind of Bayesian inverse undo the encoding. We're going to just assume there's a fixed decoder, and I'll show you also what that looks like maybe if implemented in a kind of neural network architecture. I also want to point out that this optimal coarse grading map, because it maps from one space to the same space, it can be interpreted as a kind of optimal either diffusion or maybe some kind of optimal renormalization, right? Because it's mapping to the same space, and as we'll see, it's also preserves the meaning of that space. So the coarse grainings are going to be basically interpretable in the same sense that the original inputs are interpretable. And it's a standard rate distortion problem. And so it has a convex objective, and there's fast ways to solve it to reach global optimality. Now, let me mention two things. So first, I think it's kind of interesting to point out that Bialik and Tishby and Pereira, when they introduced information bottleneck, they said, oh, we have to kind of change rate distortion because we don't have a distortion function, but we care about predicting a side variable. But we see that if that's actually the goal, we don't have to change rate distortion. There's no problem in using rate distortion with a distortion measure that's based on predicting a side random variable. We don't have to kind of change the framework. And the other thing.
Can you hear me? You said predicting a side random variable or a site random variable?
Oh, sorry. Just as so the target, let's say the target y. Okay. So a side random variable. The other thing I want to point out, and this is maybe thought for kind of also for future work, is that this is not unique. So you can imagine other. So first, let me point out that when beta goes to infinity, we recover minimal sufficient statistics. But in that sense, this distortion function is not unique, and it's not clear necessarily what is the best one. So let me just point out that, for example, this distortion function, if 1x, the predictions on y for a given x, have a different support than y given x hat, and in particular, if the support is bigger, or if the support of y given x hat is smaller than y given x, then this is going to be infinite for that pair of x and x hat. And what that means is that even as beta approaches 0, so we don't care too much about a prediction, we might imagine that this should also go to 0. But for this distortion function, it doesn't necessarily go to 0 because there's certain sort of totally incompatible inputs that will never be merged. There is a way to understand this. I can say I think it's kind of actually it makes sense why that happens, but it's not clear what is the whether that's always desirable. So maybe the optimal way to do this will have to have some kind of maybe be informed by some kind of operational setting about how we're thinking about the prediction. And actually, let me give you like what I mean by maybe one way to think about this operational setting is we can actually think of this objective in terms maybe of two coupled neural networks. So we could imagine that we have some kind of neural network or some statistical model that maps inputs to outputs. And what we want to do is we want to transmit a copy of the input to another so transmit the input to another copy of this model, and use the copy to predict the output, and then compare the predicted output to the true one using the Kolbe-Leibler divergence. So if you squint, you might see that this is basically a kind of autoencoder, right? Except we're gonna penalize the information transmission across essentially the middle of the autoencoder. And instead of having some arbitrary loss function for the autoencoder, like mean squared error or something like that, our loss function is itself going to be based on the prediction of this, what I called earlier, side random variable of prediction of the target via this network. And so also, this provides a way to basically optimize this. I mean, so, if we also hold these fixed, but map this onto, let's say, trainable network with a penalty, something maybe like variational information bottleneck, then we can in principle, at least look for numerical solutions, including for large systems. And in this picture, we can also see what is meant by the fixed decoder. So here, this decoder is fixed. We're not going to be optimizing this as we're optimizing this. And so that's why it's a much easier problem than an information bottleneck. An information bottleneck, we would also be basically optimizing this decoder to try to undo somehow the effect of the compression channel. So that's kind of the introduction to the high level idea. Let me give you a little quick example. And I'm already at half an hour, so I'm gonna go. I'm gonna wrap up pretty soon. So I considered uh random walker in 2D. It's like a 2D maze with these walls. And as the input, we're going to look at the current location of the random walker. And as the output, y, the target, we're going to try to predict the location at time 10 time steps later, let's say. And we can actually, solve the rate distortion problem for this setting. We see that there's a trade-off between compression and distortion, as might be imagined, but we can also visualize these coarse graining maps because, they map to the same space. They basically map to the space of states that we started with. And so we see that as when beta is large, we really don't compress very much. So if we start, if the actual input is the walker located here, it's going to basically like barely blur it. But as beta decreases, so we are going to want to have a more coarse grained representation. So the location basically slowly spreads out. Not totally evenly, because some directions basically are, let's say, easier to coarse grain without messing up predictions of the future than others. So, in terms of, let's say, locations within the room, and then at some point it leaves the room and it spreads out through the whole space. So we can try different starting locations, and we can see how those are coarse grained. And so this is just yet another one. And so another thing that we can do is, this is something I mentioned, is that this may give us some idea of finding somehow natural scales in the system, is we can look at how the compression and distortion cost vary with beta, the trade-off parameter, and we can look for, let's say, local, let's say, peaks in the derivatives or local troughs in the derivatives. So basically, this is where, let's say, changing the trade-off between compression and distortion by a little bit changes our predictions by a lot. And if we kind of squint at this, we can try to interpret these peaks as maybe corresponding to the point, sort of characteristic room sizes or something like that. This is maybe work to do or work to explore more. Is there any questions maybe at this point, now that I have these plots up?
About the plots or in general? Because
maybe in,
yeah, I'll just.
Maybe in general, I'm almost done, so maybe I'll finish. There's another way to generalize this objective, which is based on optimal transport. It's similar. For interest of time, I won't go into it, but I will if you ask me. So please feel free to ask me about it. And I just want to say that this slightly different formulation, which is closely related to rate distortion, one advantage of it is it has a very nice tractable convex dual formulation that gives us a kind of potential for different locations in the input state space. And this potential can be seen as a kind of cost of coarse graining a certain state. And so I'll just tell you that if I solve this slightly different problem and plot the cost, then something kind of interesting emerges, which is that it seems like the locations with the highest, let's say, cost for coarse grading are ones that correspond to doorways or narrow passages. And so I think this is kind of interesting because I think it's sort of picking up locations where, let's say, a little bit of blurring does a, has a high penalty, or another way of saying it is, your futures look very different in these locations, depending on whether you go left, right, top, bottom. You end up, let's say, in different rooms for a while. So it's kind of maybe, I think of it maybe that it has some relationship to work on things like empowerment by Daniel Polanyi and others. So I can, talk more about this if you're interested. So let me just mention a few directions. So one of the ones I've been thinking about is whether we can actually think of Bayesian inference as a kind of rate distortion. And what I mean by that is that there's something called, I believe it's called the Bayesian kernel sometimes in the literature, which is we can have a kind of coarse graining map from x to x hat, which is just defined in terms of Bayesian inference of y. So here what I mean is we generate n, let's say, independent samples of y from x, and then we calculate the posterior over x hat given those samples. Okay, so this is basically saying, given that the true data is generated from X, what's the probability that Bayesian learner will mistake the data as coming from X hat? And this is kind of a very, I think, interesting process, because when n is 0, this is just the prior, basically. So this has no information. And as n goes to infinity, this recovers, it turns out, the minimal sufficient statistics, because if two distributions are at all distinguishable, then it's going to concentrate on the basically just the ones that give exactly the same predictions. And it's kind of interesting whether we can relate to this rate distortion, whether we can think of this maybe in some limit as the solution to a rate distortion problem, which could be useful, for example, for doing things like approximate Bayesian inference, or maybe for predicting like let's say what a transformer should believe with limited data, or maybe both, which would be quite an interesting link. So that's kind of something I've been thinking about. There's also beyond that, beyond that, there's kind of some basic questions or basic things to do, like work this out for some realistic models, derive. I think this can be solved for in the case of Gaussian. So it'd be interesting to solve and look at the difference with information bottleneck, where we also have solutions for Gaussians. Think about phase transitions, see if there are phase transitions in this problem, and also relate to more standard renormalization group methods in physics, I think would be interesting. So, okay, I think, and optimal transport I mentioned briefly. There's another thing which I didn't mention, which is, I talked about basically aligning an input to itself in some sense, coarse graining, but we can also think about different spaces. So we can align, using this method, we can align, for example, audio to visual data, using actually a very small generalization of what I talked about. So that's going to be everything I want to say for now. And I think we can take a few questions, maybe.
Thanks, that was really interesting.
Yeah, I was interested in how you think about convexity. I guess, I mean, in these examples, I guess you're solving it exactly. You have the number of variables. It's just the number of pixels. But I wonder for high dimensional systems where the probability distribution is even more huge.
Right.
Do you think convexity matters in this case, and how does convexity relate to what we care about?
Yeah. So that's a great question. That's a really great question, and that's something I think it's like in some sense one of the things that we learn maybe are learning right from the recent success of deep learning and all this machine learning work is that convexity does in some sense doesn't matter as much as we thought, in the sense that really, really large neural networks are going to be basically they're just going to have saddle points, and maybe stochastic gradient descent can escape those saddle points. And so I think there's definitely been a shift in thinking less about convexity. I do think that even to start, for example, to start kind of from toy models or minimal examples, it helps to have certain guarantees or to know, for example, when you're at the optimum representation and so on. So I think that's what I would say. I think in practice, in practice, I think maybe like the more important issue is this lack of interpretability of Q in the information bottleneck. But convexity, I think, can also be important when we get started on sort of looking at toy problems. I will say that one other thing, which is, for example, both everything I said with the rate distortion and information bottleneck, they require you to basically optimize this like conditional probability distribution over what could be also a very, very large dimensional space. And that's often not really tractable. Like it's difficult to represent that, or for large spaces, not even enumerable. Effectively, we cannot actually enumerate that conditional probability distribution. So I think one of the advantages of, for example, the optimal transport formulation, which I didn't get into very deeply, is that it gives us this dual formulation, which is like an unconstrained optimization problem over a smaller space. And that smaller space can be parameterized with, let's say, neural network. So because it's basically like a function over a constraint of function over states. So that's another way that I think the non-convexity of the information bottleneck objective could actually be a barrier to, for example, having a nice dual formulation.
Yeah, that's interesting. Yeah, I might ask also about more about the optimal transport then, though I don't know if there are other questions. Yeah, I'm interested in how that.
Yeah, let me. That's it.
In particular, why is it representable by neural network while the other one is harder to represent? Is that what you said? Well,
yes, I think so. I mean, I don't know. I don't have a proof, but maybe I can show. I can share my screen again. So
might it also be useful for the toy models where like we might get like a certificate of the minimality with some dual idea?
You mean for the information bottleneck, or
you using the optimal transport objective?
You're right. I mean, the optimal transport is right. I mean, the optimal transport is a convex formulation. So like we know that the primal and the dual will be the same. But let me go over that. So I don't know how many of you are familiar with optimal transport. It's actually not so important to be familiar with it. I'll just because this is also so let me actually start from this. So optimal transport generally is a way to define a kind of, typically it's thought of as a way to define a distance between two distributions that's based on some kind of operational measure of cost or loss or cost of transporting, let's say, outcomes of one space to another space. And here we're gonna look at something called entropic optimal transport, or sometimes called sinkhorn distance, where in addition to minimizing this distortion, this average distortion across a joint distribution between two marginals, we're also going to penalize the mutual information across that. So this is sometimes called sinc horn distance. It turns out that it actually makes the problem much better behaved, and so it's used a lot in practice to solve optimal transport, but also has a kind of information theoretic flavor. Here we're gonna do this. It's kind of funny because we're gonna, gonna look for the let's say optimal transport distance between P of X and P of X and itself. So, which is, from an optimal transport perspective, it's kind of funny because usually this would just be 0.
Yeah.
But we're gonna pose this constraint. So we're gonna say, no, we can't just do an identity map. So there's a communication kind of constraint. One way to think about, so if we do this, this is equivalent to the same objective that we had before, but in addition, we're gonna constrain the marginal distribution over the coarse graining to be the same as the original one.
Yeah. So the kernel x to x is just the identity, but the kernel x to x hat varies. Is that the optimization problem?
Like if we didn't have this part,
Yeah.
this would be regular optimal transport, and then
Yeah.
the distance should vanish. I mean, typically x comma x vanishes, so this would just be minimized by the identity.
You're like trying
But-
to blur. You're trying to maximally blur X itself while retaining as much information.
Right.
Yeah.
But also if we think of this is kind of, this is very similar to the objective we had. Well, I won't go back. This is very similar with the objective we had, rate distortion, except we're just going to say, no, once we blur, right, we want to recover the same distribution as at the beginning. Another way of saying that is we want a coarse graining map such that also the input distribution is actually like in steady state for that, or we want a flow such that the input distribution is in steady state for that flow, is stationary under that flow. So if we do this, if we add this constraint, in a way, it actually simplifies the problem because it simplifies especially this term because we don't have to marginalize in this term. And we can write the problem in this dual form where we optimize over basically two potentials. So this is a smaller space. Now this is going to be like, 2 n variables rather than n squared variables. And they're not constrained. So this is the convex dual of that problem. And so we can just optimize over these potentials. Now, these potentials themselves, for example, in a continuous or a very large discrete space could be parameterized by a neural network, right? So these are just functions of X.
Yeah, I think I don't see exactly where these potentials are coming from.
I mean, I think if you're, I mean, it takes a little bit of
maybe
of
I'll think
algebra,
about
but this is if you're familiar with convex duality, it's basically derived by convex duality. So these are the Lagrange multipliers that enforce that basically enforce these marginal constraints.
So is one of the variables?
Oh,
adjoint?
I see. Yeah.
Is there an adjoint variable? Who is adjoint?
So the constraints are that both marginals are equal to px. Right? That's the constraints. So this has so these are the two adjoint Lagrange multipliers for those constraints.
Phi and phi. Okay, phi is adjoint to X and psi is to X hat.
Yeah. Yeah. I mean, yes. Right. Phi is to X and psi is to X hat. And this is maybe I should say lower dimensional unconstrained optimization. We can recover the optimal map from these if we wish. But in optimal transport, these are called the Kantorovich potentials. They have actually a beautiful interpretation in regular optimal transport, which I can tell you. So in regular optimal transport, these dual potentials are basically like, so they tell you the following. So in optimal transport, as you probably, if you've heard anything about it, you've heard the thing about like you have factories and you have shops and you want to transport goods from factories to goods in shops, and there's some cost to transporting, based, let's say, on the distance between the factory and the shops. So that's the primal problem. You minimize this coupling between the shops and the factories and you minimize the expected cost. But the Koncharovich potentials say that instead of transporting anything at all, you can just like sell the stuff locally at the factories and buy the things locally at the shops, right? At the local market, and the price you should pay for those goods are these. The price you should sell or buy are these. In our case, these are quantify the susceptibility of the objective to increasing the probability of the walker, let's say in my example, the walker being in a certain state. So that's why I said that these are kind of give us a notion of which states are more costly, because they basically say, if I increase the probability, the percentage of the time that the walker is in a given state, how much does the cost go up? And so that's a kind of natural way to quantify, which states are worse. Yeah. And this is one of the potentials. In my case, numerically, and I think there's probably a way to show this is more general. In my case, the potentials are equal to each other numerically. So I think it could be reduced to maybe a single potential.
You had like two scales in this setup, right? There's the R, the small scale, and then the beta. I'm guessing R should be small, but could you play with this?
Sorry, R being the time lag, or
the amount of blurring between X and X star.
So beta is dual to R.
Okay.
So beta controls right. So beta is the Lagrange multiplier corresponding to, or 1 over beta would be. So beta is equivalent to R. But there is another scale in this problem, which is implicitly, right? Because I said, okay, just for this toy example, like what we want to predict is the location of the walker in 10 time steps. That's also another kind of scale, because we're sort of saying, right, for obvious reasons. I think that, the longer if you predict just infinitely into the future, there's actually nothing to predict because you always go to the steady state. So it's kind of interesting, and I don't know, I'm not sure how to think about the interplay between these two scales in this toy example.
I'd like to hear more about the relation to empowerment that you mentioned.
So let me so okay, so basically I think I can just say it. So this is more of a hint, and this is also based on some I don't know, maybe I know some of you were at the Iliad 2 conference in Berkeley about 2 months ago, a month and a half ago. And Stas Tiomkin gave a talk about kind of empowerment. And so I thought it was very interesting. But basically, empowerment is this idea that you want to go to states where, to put it simply, you have many futures available to you, right? Or you can essentially maybe reach many different outcomes from those states. And those are the states with high empowerment. And that's a kind of intrinsic goal maybe for agents that you can train agents on. So I actually think maybe that I showed this map where the potential is large, which seems to correspond to things like doors. So those are also normally would be what we consider as locations of large empowerment, because if you're at a door, this gives you a much easier way to access some multiple different futures, which is I think it's actually kind of similar. It's like, locations with high empowerment, it's also in some ways, it's they're maybe we could say they're harder to coarse grain, because you don't know where you'll end up, right? Or where an agent in high empowerment will end up, as opposed to, somebody stuck in like a dungeon or something where it's a very low empowerment state. They cannot escape, they cannot go anywhere. Like there's very little that we can kind of completely coarse grain, if we want to predict their future. So I think there's uh and I talked a little bit to Stas about whether this dual formulation could be used as a way to calculate empowerment. I think one of the problems is empowerment is difficult to calculate, but I haven't pushed much deeper than what I just said into that kind of connection.
I have one more question, if no one else has. So yesterday we were discussing synthetic data and what we need to reliably test theoretical assumptions. So I'm curious if you have any, I don't know, dream data sets or ideal data sets that you'd like to see.
Well, that's interesting. I mean, so it's not okay. So that's not exactly an answer to your question, but I think something that would be useful to think about is if we want to use this for, let's say, AI alignment, and let's say I take uh some kind of large or reasonably large like LLM or something, and I think we could do this. I think we could get some kind of coarse graining at multiple scales. And I guess one thing that I think would be, yeah, this is not exactly, I mean, so I think that would be interesting to play around with. Or it doesn't even have to be a very complicated model, but it would be interesting to get started with. But then we might say, okay, well, how do we then kind of interpret these coarse graining? So I showed that, I mean, for a walker, we can 2D walker, we can show a map of how it's coarse grained. For, let's say, internal representations, we can produce effectively like like we can sample other internal representations that are approximately in the same equivalence class, like approximately give the same predictions, let's say. And but then how do we interpret that, I guess? Would that be useful in itself to just sort of say, okay, so that's one thing I'm kind of thinking about, is it's related to what kind of data would be useful, but I'm also kind of thinking about how you would interpret the outcomes.
You briefly mentioned that one of the potential future directions can be a connection to RG flows and fixed points. What can be advantages of finding such fixed points in this information theoretic flow, and if you combine it with RG?
Yeah, that's interesting question. So let me mention two things. So I think one of them is uh I mentioned kind of, if we can think of maybe we can think of iterating. So we can think of another way of kind of coarse graining, right? Different scales is, let's say we find this kind of optimal diffusion at for a given beta, and then we just like iterate it, right, over and over and over again, and eventually it's going to blur out and it's going to go to the fixed point. And so now we're not increasing beta necessarily, we're just kind of like, like we're thinking of coarse graining as diffusion, and we're running it forward. And in the limit, we can even imagine considering like the short time limit, where we try to find, let's say, the infinitesimal generator that then could be run and give us some multi-scale coarse graining. So I mean, I think one, this could be just interesting to see if it can be done. Two, it could be at least numerically advantageous, because you don't have to solve the problem for each beta, you just solve it once, and then you get like the whole multi-scale decomposition. The other thing, so that's kind of one thing that I was thinking about. The other thing is, in renormalization in physics. So once you get this usually continuous time flow, and then you look for fixed points, you recover things like critical points and phases. And one might ask if something similar would happen in like some kind of in other settings, in non-physical settings, whether we could recover different phases or fixed points or critical points based on how they coarse grain.
That makes sense. Thank you.